Calculus 3.6. This is a summary of all of lessons. Basically, everything we've done this year at this point is all going to be combined in today's lesson. So it's kind of like a mixed review. If we were asked to sketch a graph of a function either by hand or a graphing calculator, remember that normally you cannot show an entire graph. But by seeing both views here, for instance, on this function, if I was asked to graph it, this is what my calculator shows for the windows -2 to 5 and -10 to 40. If I change the view from -10 to 30 and y is -1200 to 200, and now look at my graph. See, sometimes we have to use calculus, or we need to at least use common sense and know that this right here would be a bad picture for this graph. And next to the third graph should have an end behavior of down and up, and this did not even show that. So sometimes we need calculus, so therefore we know we get the best picture of our graph. So here we go. We need to analyze, we need to sketch the graph of this function. First off, what's my domain? Always ask about what that domain is first. All right, so what's going to happen on your test for me? I'm going to give you a function like this. You are going to answer all of these questions about that function and draw the graph. It's going to be worth 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, plus the graph, plus the derivatives. So this is about a 20-point question on the test. I usually like to give 2 of these. Hopefully you're good with the first derivative. That would have been a low d high minus a high d low over low squared. Simplify it. Then when you take this derivative to get the second, again, you would do another low d high d low, low squared, and simplify it as well. If you need help with that, ask me. We've covered that in several videos prior to. So today's just about how do we put it all together. All right, so my x-intercepts would mean to find x when y is 0. Well, the only time y can be 0 is if that numerator is 0. So that's going to be 3 and -3. My y-intercept means to find y when x is 0. So if x is 0, that'd be -18 on top. That'd be a -4 on bottom, therefore 9/2. Vertical asymptotes. Nothing factors and cancels, so my vertical asymptotes are x equals 2 and -2. My horizontal asymptotes. Bobo or Betsy? Oh, if you're thinking we got Betsy, we got 2x squared, we got an x squared, so it'd be y equals 2 for my horizontal asymptote. Critical numbers, that comes from the first derivative equals 0 or undefined. But in this situation, it's 0 from the top is 0, but the bottom gave me 2 and -2. But remember, those critical numbers, I would have to throw out this -2 and 2 because those are not in my original domain. So in your copy of notes, please go ahead and cross out that 2 and -2. Those are not critical numbers. Again, the critical numbers can be when the first derivative is 0 or undefined, but the numbers need to be in the domain to start with. So those were not in the domain, so you will want to cross those out. All right, so for max and mins, notice my -2 and 2, I did those a red dotted line because those will represent my asymptotes. X equals 0 was my critical value. I need to plug in around all of these to see if it's positive or negative. Now, when I take a look at this denominator, it's always positive no matter what I plug in for x. See, x squared minus 4 could be a negative value, but when I square it, it's always positive. So I really don't even need to worry about the denominator. I just need to know if the numerator is positive or negative when I plug in, say, -3, -1, 1, and +3. So when I plug in these two negative values into 20x, these two right here will both be negative. When I plug in 1 or 3 into that first derivative, those would both be positive. So this tells me my graph is decreasing, decreasing, increasing, increasing. Here's the only place I have either a max or a min. And since it's decreasing then increasing, there's going to be a minimum at x equals 0. I have no maximums, but I have a minimum at x equals 0. All right, from the second derivative number line test, again, the denominator 2 and -2 came from the original domain. Those were dotted. That numerator can never equal 0. 3x squared plus 4 will never be 0. That is always a positive number. So therefore, I have no fake critical numbers for the second derivative. So I just need to know if the second derivative here is positive or negative along here. Now, the 3x squared plus 4 part is always positive, so I don't need that. I just need the -20 divided by this part down here on the bottom. If I start with, say, -3, square it's 9, minus 4 is 5, cubed is positive, -20 divided by positive would be negative over here to the left. Oops, I hit the wrong key. If I start with 0 in the middle, again, we're checking into the second derivative. Remember that right there was always positive. Okay, that's still -20. 0 here is 0. -4 to the third would be negative. Negative 20 divided by that negative, this is going to be positive in the middle. So my graph is concave up from negative 2 to 2. When I plug in x is 3 into the second derivative, this value is going to be negative. So my graph is concave down, concave up, concave down. I have no inflection points. So there was no maximums. We had a minimum at x equaled 0. We had no inflections. The domain, remember from the very beginning, x could not be 2 or negative 2. I hope on the test that I put domain first. I believe I did. It's easier if I do. All right, testing for symmetry. If I was to replace negative x for x, this function right here in the original actually would go back to the original function. So it is symmetric with the y-axis. So if you can replace negative x for x, it goes back to the original equation. It is symmetric with the y-axis. If it goes to the exact opposite of the original equation, it is symmetric with the origin. My graph was increasing here from 0 to 2 and 2 to infinity. You must separate those because 2 was not in the domain. It was decreasing from negative infinity to negative 2 and negative 2 to 0. Again, you must separate those because this was not in the domain. That's why I color-coded it. It was concave up from negative 2 to 2. It was concave down from the negative 2 to infinity, and negative infinity to negative 2, and then 2 to infinity. And then we draw this one on the whiteboard on the next slide. So I don't have a whiteboard, so give me just a second. So we have a, let me see, we had a no maximums. We had a minimum at 0, 9/2. So this is a minimum. We have an asymptote at x equals negative 2, at x equals positive 2. You have a horizontal asymptote at y equals positive 2. All right, first part here is decreasing. A minimum. And just a second here, guys. Sorry about that. I should have grabbed me a board. Okay, so what we have is this first part of the graph here was decreasing. Let me put something dark behind that. That's better. Okay, so from negative infinity to negative 2, my graph is decreasing and concave down. See, that tells me this part of the graph will do that. It can't be up here because that would be concave up and it would be increasing. So it's here is concave down and it is decreasing. All right, from negative 2 to 2, the graph goes from decreasing to increasing. There was a minimum there. From negative 2 to 2, the graph is concave up. Look at my graph. Boom. See, it's decreasing, increasing. There's the minimum and it's concave up. All right, this next section tells me my graph is increasing and it's concave down. It is increasing and that graph is concave down. We had the vertical asymptotes was at 2 and negative 2, so I drew those. My horizontal asymptote happened to have been y equals 2, so I did that one. This was not drawn to scale, but this was just a quick rough graph of that for you. And here's the more accurate picture of that graph. So again, there was your concave down, concave up, concave down. This piece was decreasing, decreasing, increasing, and this piece was increasing. They plotted the maximums. They plotted the x and the x-intercept here as well, the asymptote, and the two vertical ones. All right, so to find a slant asymptote of a function, we would use long division to rewrite the rational function as the sum of the first degree polynomial and another rational. Now, in this situation, I actually could have done synthetic division. If you're weak with that, ask me, and I will remind you how to do that. So with my synthetic division, I would have ended up with y equals 1x plus the remainder of 4 over x minus 2. So here would be the slant asymptote of y equals x. That's the oblique asymptote, y equals x. Okay. You have a vertical asymptote of x equals 2. It's right there. And if you had done your first derivative test and your second derivative test and all that, you would get the graph as increasing here, decreasing. You get decreasing, increasing. This would be the second derivative test. This would be concave down. This would be concave up. You would get your max there, a min here. And these are questions that I ask on the test. So again, like I said in the past, this has been either 10 to 20 points on the final exam, anywhere from 10 to 20. My test was probably about 40 points of the test will be from section 6, where you will actually fill in all this information, but I'll try to remember to move the word domain up to the top. Remember on your critical numbers, please, if it's not in the domain, to make sure you throw that out from the critical numbers, because it can't be a critical number if it's not even in the domain to start with. Other than that, guys, that's it for section 6. I did say here, first do number 16 together and discuss its asymptotes. So in class tomorrow, somebody go ahead and open up number 16 and we will work that one together as a class, and we'll discuss what's happening on that problem. Good luck to you guys. Have a great day.